Transformer architectures really lean on this idea of, for every word in, say, a sentence or a bit of text, figuring out what other words are most relevant to it. So the man saw the dog with the telescope. That can be somewhat ambiguous from just the grammar. It seems funny when I say, well, what was the dog doing with the telescope?
Today's episode of Hidden in Plain Sight is with Mike Tamir. Mike has served as head of data science at the Uber Advanced Technology Group and as a lecturer for UC Berkeley's data science program. Mike has a background in physics, and his early research focused on developing the epsilon anchor methodology for resolving an inconsistency he highlighted in the dynamics of Einstein's general relativity theory. Today we talk about his work and the state of natural language processing and understanding. We talk about GPT-2, the release of GPT-3, and what they mean for the industry. We also cover Mike's work into preventing fake news and misinformation from spreading, and get his thoughts on the future of AI and humanity. Now let's jump into today's episode of Hidden in Plain Sight with Mike Tamir.
This season of Hidden in Plain Sight is brought to you exclusively by our friends at Splunk, the Data to Everything platform. Splunk helps organizations worldwide turn data into doing. It's time for data to be more than a record of what happened. It's time to make things happen. Learn more at Splunk.com or by clicking the link in our show notes.
Mike, welcome to the show.
Thanks for having me.
So Mike, when you hear the words data science, you have a lot of experience there. Where does your mind go? You have such a broad and varied career. When people ask you what you do, when they hear data science, how do you introduce it and how do you think of that?
Certainly, for the majority of the past 10 years or so, it has been some sort of mixture of having the skills to look at and explore and work with data, in particular, being able to do the statistics, and a mixture of also being able to do the machine learning and more recently the deep learning models, being able to train them for a whole host of purposes. Now I do believe that the terminology has been shifting a bit, and for better or for worse. There terms like machine learning scientist or machine learning engineer maybe have become more appropriate for the people that work in deep learning and more traditional machine learning modeling. Unfortunately, maybe some data scientists who everyone was very quick to relabel themselves on LinkedIn, perhaps as a data scientist. As a result, I think maybe that term of art has become more relegated to more traditional analytics roles, at least at some companies, although not everywhere.
So you've worked at a number of places. You're at UC Berkeley now. You've worked at Uber, ATG. When it comes to your most recent career experiences, are there any cool things that you can share that are top of mind now or projects you think are going to impact the world in a big way soon?
The list of cool things that we can do with machines is quite large. You can't deny the progress that has been made in areas from natural language processing, being able to not just do things like embed words and figure out cute analogies, which is really where the most recent natural language understanding revolution started with word vectorization, but now can solve problems that really seemed insurmountable 10 years ago. Automated captioning, solving problems with natural language inference, although there are some famous failures or sort of foils in natural language inference tasks, doing things like automated text generation, which was pretty nascent 10 years ago, but now with transformer technology, very recently OpenAI released GPT-3. And so now the hard work of researching things like how much of this is memorization, how much of this is actual capturing of what's fundamental about language and how people speak in English in particular, but other languages. That's going to take years to start unwinding.
And when it comes to this field or those fields, what does this mean for the present of human and computer interaction and the future of it? What are some things that we can do now that we, thought were impossible 10 years ago? And where do you see them going?
Rewinding a few years from, in the year 2020, going back, maybe 4 or 5 years to, some of the gains that we are being able to make in machine translation are important. These gains really predated a lot of the transformer improvements that we've seen. Looking at abstractive summarization also is another thing that, doing anything other than extractive summarization, where you kind of like skim the article for the most important sentence that summarizes what it's talking about, or the topic type sentence or subject of the text sentence. That sort of seemed like a dark art and something that we maybe wouldn't be able to do very well. And now fast forwarding to 2020, these are things that really feels like we've gotten our arms around in terms of abstractive summarization, finding a way of capturing the body of information that is in an entire piece of text, and then boiling that down to the most important kernel that can then be written, not just in natural language, but in coherent natural language, is something that is pretty amazing.
You were working on the fake news challenge at fakerfact.org. How did that project come about, and how are you working to combat that challenge?
Right. And to clarify, there was a formal competition called the Fake News Challenge, which we've been interested in that, but we didn't participate in. The more general challenge of dealing with fake news, the benefits of sharing of resources across all over the world can't be understated. The advances that we get from open source projects, from research, from being able to take advantage of the brain power, so to speak, of efforts done by scientists throughout the world, really are something that we need to maybe appreciate more. That being said, it's also very easy to share. The low friction of sharing information also means the low friction of sharing maybe information or manipulative information, and that's something that obviously has been a hot topic for the past 4 years in particular, since around 2016, and so when we first start thinking about this project, the goal was not necessarily to figure out how you can use machine learning or automated methodologies in general to attack the problem of truth detection. The much more modest challenge is trying to just figure out what sorts of patterns of language, or can you create in an automated way algorithms that can detect what sorts of patterns of language are more commonly seen in text that is, as I mentioned, scientifically focused on in the sorts of things that you see in Wikipedia articles and scientific journals, in more, maybe you might call it dry or less rhetorically thick news organizations, mediums for sharing information that might actually have a hidden bias, or at least a hidden agenda that us as humans, and for probably very good reasons, are interested in maybe not overthinking the information that we're presented with when it is laden with certain kinds of triggers, emotional triggers, things that make us angry, upset, afraid, have a sense of urgency. And as a result, actually the psychological studies tend to reveal that our cognitive abilities end up getting suppressed when in the presence of those sorts of emotional triggers. And so one of the hypotheses that really drove our project was this hypothesis that if we can detect those sorts of emotionally triggering language, maybe there's a correlation between the so-called true blue information sharing text versus text that maybe does have that sort of hidden agenda. And instead of, like I said, trying to create an automated truth detector, we ended up focusing on that other axis, that of what text is emotionally manipulative versus not, and sort of leaning on that correlation in terms of whether or not that's going to help detect truth or falsity in the text.
Yeah, that's very exciting. And moving away from a world where, people are ostensibly getting information and news, but just really going into these cycles of repetition compulsion and just triggering themselves. We've got to get away from that. And I think that's one area where tools like GPT-3 and some of the natural language understanding processes you're talking about are going to be critical. So, Mike, on a previous podcast episode, we talked a little bit about GPT-2, but I'd be curious to get your take on GPT-3. You mentioned that all the different parameters that it uses. But for those of us that aren't familiar with the tool, why is it significant and how is it a step up from GPT-2?
Full disclosure, I don't work for OpenAI. I can give my perspective of the algorithm maybe as a somewhat outsider from that organization. GPT-3, like I mentioned, is roughly 170 billion parameters. Perhaps the largest model in natural language that I know of. Certainly the largest model with a transformer style architecture. And just for I've mentioned transformer architectures quite a bit. The very, very short summary of what those architectures are all about is that when we cracked open this challenge of abstractive summarization, being able to figure out how to find what's important in text without just cutting and pasting the most important sentence, really the key insight, or one of the driving techniques for starting to solve that problem in neural machine translation as well, was this idea of attention, of figuring out how to take one word, for instance, or when you're writing an answer, translation or whatever it is, and seeing what's most important, what's the most relevant part of the source text to that next word vector, for instance. And these attention mechanisms ended up being a very effective trick for that. Transformer architectures really lean on this idea of, for every word in, say, a sentence or a bit of text, figuring out what other words are most relevant to it. So the man saw the dog with the telescope. That can be somewhat ambiguous from just the grammar. It seems funny when I say, well, what was the dog doing with the telescope? The man is the one using the telescope, not the dog. And by using these self-attention networks, it's multi-headed self-attention networks, in very, heavily, not only did that allow us to get away from these fundamentally sequential techniques like recurrent neural networks that kind of had to look at each word one word at a time in sequence, but looking at them, all at once. This has a lot of benefits in terms of training time. So you can feed all of that information into the GPU in parallel and train quite a bit faster.
And Mike, your background is broad, it's in mathematics and in physics. Would you be willing to kind of talk about and unpack your research on the epsilon anchor methodology as it relates to Einstein's general relativity theory? I know it's a broad and deep concept, but I think that's very interesting and would love to hear you talk on it.
I also was part of a philosophy of physics program, a pretty technical philosophy of physics program. And so, that field really is rewarded for writing about very technical problems with things that physicists are able to accomplish, and picking on them sort of mercilessly. And so I guess maybe a good example of this would be the Dirac delta. Dirac came up with the Dirac delta, and it worked really great in physics for dozens of years before anybody invented Sobolev spaces and distribution theory to actually put it on a firm mathematical footing. The thing that I picked on in general relativity is this, sort of a parallel to what happens in electromagnetism, electrodynamics, particularly classical electrodynamics. So maybe we could think about that because it might be a little bit easier to start. When you have
Sure.
an electron moving through a electromagnetic field, we have different equations like Coulomb's law and things that you might have learned in high school physics that sort of describe the forces that would act on this electron, this, or maybe this. Sometimes you call it a test particle with a test charge. And I'm going to put some quotes around that test particle idea. And so it'll move around. It's going to. There's a magnetic force. It's going to move due to magnetic forces, and electric field is going to move due to the electric forces, and so those forces are going to define a path for that test particle. Except that in order to react to that electromagnetic field, the test particle is going to have a charge itself. And as we may remember from high school physics, a moving charge creates its own electromagnetic field, in particular magnetic field. And so there's going to be a self field that it's creating due to the movement that it is doing in reacting to that field. And so now it has to react not only to that field that was there to start, so to speak, but also to the field that it creates. And then that's going to change the movement. And so it's impossible to come up with a closed form solution to that. You end up a lot of a sequence of approximations. And so this is called the self-force problem. Now, this has been a very well studied and discussed problem in electrodynamics for years, and the same thing happens in general relativity, or a very similar kind of phenomenon. You have a body, and that body is reacting to space-time curvature, gravity, and so is going to move in a certain way. But because it is a massive object and reacting to that space-time curvature, it's going to warp space-time itself as it moves. And so you add a little bit of wibble wobble to to how that body is going to move. And so maybe the most dramatic way to say why this is problematic is when Einstein discovered the general theory of relativity, his theory of gravitation, there was ostensibly two equations. One is the equation, the Einstein's equation, that says that the stress energy is related to the Einstein curvature, and then there was a sort of like other equation that maybe was given a little bit more importance than it deserved as a fundamental equation called the geodesic principle. And the geodesic principle basically says you have this manifold of warped space-time, and massive bodies will follow the shortest path in a curved space-time, called the geodesic path. Geodesic paths in a perfectly flat space-time are those straight lines. Geodesic paths in a curved time might be like an orbit around the sun, for instance, right? So the way that the Earth moves around the sun is a geodesic path, approximately. And Einstein's ostensibly one of the greatest moments of scientific discovery in his life was when he realized that by using these two equations, he was able to predict a problem in gravitational theory that had existed since Newton, namely, Newton's equations for gravitation were able to predict the motion of all the heavenly bodies except for one. Except for Mercury. Mercury sort of goes around the sun, and like all the planets in the solar system, it's a little bit more elliptical than maybe we want it to be. It's not perfectly spherical, and then the way that ellipse kind of rotates around was you couldn't explain it with these classical non-relativistic equations, but with the geodesic principle, you could explain it. And so this made I remember reading from Einstein's notes about his discovery. He said he had heart palpitations. This was like a wonderful discovery. Using the geodesic principle, he had to sit down. This was he had solved the problem, the thing that Newton couldn't do with Newtonian gravitation. And of course the very picky thing that I did was was saying, well, not quite. There's a little bit of wibble wobble there. And of course, I think that the very fair thing is to say that this is so small, it's certainly unobservable. If you want to be not picky, obviously Einstein solved that problem, but not perfectly with the geodesic equation. The geodesic equation is just an anchor of how massive bodies react to much more massive bodies, and there, what you have to do is, in order to make sense of why a false sort of thing, a prediction, like an idealized prediction, that which the geodesic principle really is. It's an idealization of how massive bodies move, not a real prediction, not a perfectly veridical prediction. You need to show some sort of connection between the way you make your predictions that are not true, if you did it really in the right way, and so that has to do with picking the right topological spaces and showing that there are like epsilon delta relationships. When you turn down this side of your assumptions, then you're going to turn down this side of your errors. That's really where that idea comes from.
Wow, thank you for taking the time to unpack that. Really, really interesting work. And Mike, you mentioned earlier that you had a chance to interact with a lot of different philosophers and ethicists, and where we're at, I feel like in the field and as it relates to the future of technology, is this place where ethics matter more than ever. Are there any really interesting ideas that you remember from your discussions with these philosophers and these folks that you feel like you wish were in the current debate about technology, about data science? What big ideas do we need to get out there as it relates to ethics?
Peter Singer has this article, much more well known for convincing people about the ethical reasons for not eating animals, but also has a less well known discussion about whether or not robots should have rights. I forget the exact title of the paper. There are a lot of important questions, like what it takes to be a person, and what it takes to have rights, and what it takes to have knowledge and understanding. And these questions are questions that philosophers have, at least before digital media became most popular. A lot of trees have died in the effort to discuss these ideas. We're going pretty quickly. Having had the pleasure of being part of this field for the past decade, it's been exciting to see how fast things progress, and how much faster things progress than even my most optimistic expectations. And if that trend continues, I don't think it's perfectly unreasonable to think that one day that question of how do we think about intelligence that is not biological will not just be a perfectly hypothetical one. And maybe there are certainly reasons to think that it may not ever become important, but it seems like something that will have a lot more relevance potentially than it has ever had in the past.
Amazing perspective. And Mike, thanks again so much for your time. And to everyone listening, we will see you next time.
Thank you.
I'm Sophia Bush, and you've been listening to Hidden in Plain Sight from Mission.org. This podcast is sponsored by our friends at Splunk, the Data to Everything platform. In today's data-driven world, every company, big or small, new or old, is sitting on terabytes of unused, untapped, and unknown data. Splunk helps turn all that data into action. Using cutting-edge AI and machine learning, Splunk delivers real-time predictive insights that will help you on your mission to change the world. With solutions for IT, security, Internet of Things, and business operations, Splunk empowers people to make faster, better decisions and take action to get things done. It's time for our data to be more than a record of what happened. It's time to make things happen. Check it out at Splunk.com.